My name is Chad Boyd. I've been giving some SQL presentations yesterday and today. This is my last one. Last one for you guys for today as well, so I'll try not to keep you here too long. But we're going to talk about solid-state drives and flash storage today and the impact that those will have primarily on SQL Server, but we'll also discuss general application usages. My guess is that most people here are developers, as opposed to administrators and architects. Yeah, any administrators? That's what I figured. So we're going to cover some discussion of the impact of solid-state drive on traditional application workloads as well, similar to just the Windows OS or custom applications that you might write today, and how that or how solid-state impacts I/O as a whole. So we're going to hit on a couple different things. First thing we're going to cover is what a solid-state drive actually is. We're going to cover some of the benefits. We'll talk through some of the different types of I/O and which applications and what types of operations they apply to. Specifically with SQL Server, there's drastically different patterns and usages for different data files and different configurations, et cetera, et cetera. The same would hold true for the Windows OS as a whole. We're going to compare solid-state to your traditional hard disk drives in both scenarios, traditional applications as well as SQL Server. I do have a lot more performance and scenario-based information regarding SQL Server, but it would also apply to traditional applications that generate the same types of I/O patterns and sizes as well. We're going to talk about some of the trends in the industry that are actually benefiting solid-state drives. There's actually quite a few trends today, many that I'm sure you could think of off the top of your head, maybe a couple that don't come to mind right off the bat. And then we'll map all that stuff to SQL Server specifically. So what is a solid-state drive? Well, your traditional hard drive is made up of a platter and spindle. It looks like a record player, basically, underneath. Has everybody here ever seen a physical hard drive? Know what it looks like? So you know that there's physical moving hardware. You've got a platter that spins, and you've got a disk arm that moves left and right. So that's latency and seek time. So anytime you submit an I/O request to a particular spindle, that platter has to spin and that I/O arm has to move. We'll talk about that throughout the presentation. Solid-state drives, on the other hand, are non-mechanical with no physical parts. They're basically a semiconductor technology. They use flash media to store your data. So given that there's no moving parts, that alone should tell you that reliability of a solid-state drive is much higher than your traditional hard disk drive today. Anytime you introduce moving parts into anything, whether it's computer technology or anything that humans would make, you're introducing error possibilities. So the fact that there's no moving parts increases the reliability right off the bat. Things, both reliability, but as well in terms of power consumption, heat dissipation, and the fact that it can withstand not only higher and lower temperatures, but also more vibration, more stress, given that mostly because there's no moving parts. And I'll show you a small video of that here in a bit. Power consumption, again, no moving parts. Power consumption is extremely low. I'll show you a chart that lays the differences out. Performance is much higher. We'll discuss that as well. And heat generation is lower. Again, mostly because of the fact that there's no moving parts. Okay? The one downside, or the biggest downside, not the only one, but the biggest downside to solid-state drives and flash technology today, particularly in commodity hardware like laptops and as well in broad enterprise adoption, is the fact that the cost to the storage capacity ratio is still pretty high. So your cost per gigabyte is much higher than your traditional like SATA 2 drives today, particularly the ones that, you've got SATA drives today that push 1 terabyte or more on a single platter. So for a very low cost. A quick chart to highlight the adoption of solid-state drives and flash technology in the industry today. You can see back in 2006 there were very few. That's projected to exceed in 2011, go off the charts basically. These are units in millions of dollars. It's projected in 2011 there's going to be just under 35 million units sold. So the adoption of solid state in the industry is taking off, but in the next few slides, as you can probably figure out, a lot of that isn't driven from, again, your enterprise storage platforms or your commodity hardware like a laptop. It's more from like your mobile devices. All your mobile devices, iPhones, iPods, Zooms, mobile phones, things like that, those all use some form of flash or solid state technology for storing how much of the data you can store. So let's discuss some of the different types of I/O. There's two big types of I/O, random and sequential, and then two drastically different patterns of I/O. Random I/O, as you can see on screen, is your small, short bursts of I/O for relatively small amounts of data that are spread across the disk or spread across multiple disks. Okay, give me this record from a database, or give me this section from a configuration file. Or at the OS level, it could be write this section of memory to the page file so I can free up room for this other application that needs memory now. That's all your random I/O. DLLs are actually heavily random I/O. So in your app dev world, even though DLLs are encapsulated in a single file and are typically contiguous on your disk, when a DLL is loaded or accessed, that's typically accessed in anywhere between 5 and 15 random I/Os as opposed to one sequential I/O. Some of that has to do with the memory architecture of the Windows platform. Some of that has to do with just development practices in general. Registry access and all your system metadata, that's typically 99% random I/O access. Sequential I/O, on the other hand, you see it at times such as boot up. One big sequential I/O operation that happens on typically every boot is the initialization of your page file. Okay, so if you have a page file that's set to on many servers, on 64-bit servers today, you might have a page file that's set to grow to 10, 20, 50, or 100 gigabytes on boot. That's one very large sequential operation, or many very large sequential operations. Anytime you hibernate and wake up, it's very similar to a boot process, minus your page file. And then your application load and your document load. So if you open up a Word document, there's typically large sequential I/O operations there, or PDF files. Or if you fire up an application, typical applications that you might write yourself, or any off-the-shelf application that you might run on your PC. Those are typically generate higher numbers of sequential I/Os. Once they're running, then small amounts of random I/Os fire very frequently. Okay. So these traditional types of applications, whether it's custom built or third party or built into your OS platform, hard drive performance really is typically measured in the number of I/O operations per second, as opposed to your overall transfer rate. You might have a hard drive and a controller that can support 3 gigabits of throughput per second, but that really doesn't matter if you're firing 1,000 random I/Os, because you're not going to come close to touching that max data transfer rate. You just want those small I/Os to fire as fast as possible to give a faster response time to the end user. So in your typical app dev type scenarios or OS type applications, you'll sacrifice the transfer rate for a higher number of I/O operations per second most any day. Now, in the database world, as we'll talk about here in a bit, that's totally different. One thing to note is that in a typical hard drive, typical traditional hard drive today, it could be a SATA, it could be SAS, it could be whatever, but they can perform anywhere from 4 to in some cases, even 128 kilobytes of data access in the same time, in the same amount of time they can pull in 8K. If you have a sequential operation that pulls a single I/O operation that pulls 128K of data versus 8K of data, they'll finish in almost the exact same time if that 128K of data is contiguous on disk. Why is that? Because 95 to 99 almost % of the time for I/O access on a traditional hard drive spindle is the platter spinning and the arm moving. Okay, the actual time to transfer the data from the drive to the OS is very minimal compared to the time it takes those mechanical pieces to spin and swing back and forth. Okay. OS transfers, you can see here we talked about random and sequential. You obviously also have reads and writes. So you have random reads and random writes, sequential reads and sequential writes. On a traditional OS platform or app dev type application, random reads will typically account for over half the total I/O operations that you're going to perform. Okay. Random writes will account for another 10 to 15%. Now these are your traditional applications that run on your OS or app dev type application. So those random access type operations account for anywhere from 60 to 75 or 80% of the I/O operations that you're actually doing. I guess this is just another graph to show you that this is Vista in particular, 4 to 8K reads account for over half of the total read transfers in a typical user session. So to kind of back up or to reiterate a lot of the things that we've talked about, on the left here you've got a standard, a commodity solid state drive today. I believe this is based on the Samsung solid state drive. And a traditional 3 gigabit hard disk drive. You can see the different mechanism types. You can see the operating temperatures. The disk drive over here is generally higher operating temperature than your solid state drive. Noise from your solid state drive is nil. Noise from a typical hard drive most of the time is relatively low. I put 0.x because it could be anywhere from 0.001 to 0.4. If you're running a large sequential write, it's usually louder than if you're just idling in a PowerPoint presentation. If you've ever been sitting somewhere and your disk and your computer's sitting next to you and it starts kicking off a backup or something, and you start hearing that sound and that noise in the background, a lot of that's the fan, and sometimes the hard drive as well. Performance is a big one. Your solid state drives can typically sustain a random read of 100 megabytes per second. Contrast that with your typical SATA drive today, which is 59 megabytes per second. That's nearly double of the solid state drive. Your writes, your solid state drives can typically sustain anywhere from 60 to 80 is kind of the high end. And your SATA drives can sustain typically around 60 megabytes per second. Now that's mostly random I/O. We'll talk about some sequential differences as we get to the SQL Server specific things here in a minute. Your seek time on a solid state drive is fixed. It never changes. You could access data from anywhere on the drive, and it's going to take you 0.11 milliseconds right now, or whatever the manufacturer's specification is. It does not change. Unlike your typical hard drive platter today, it's variable. If the drive is already in the location for the data you're trying to access, you're going to have a very low seek time because the platter and the spindle doesn't have to move. As soon as that platter and spindle has to move, you're going to drive up your seek time. Power consumption is a big one. This particular solid state drive takes 1 watt of power when it's active, 0.1 watts idle, even less when it's hibernating or off or on standby. Compare that to your traditional SATA spindle, and it's just under 4 times active and quite a bit more when it's even idle. So power consumption is much higher than your traditional spindles that your solid state. Operating vibration, you can see that your solid state can withstand a vibration that's exponentially larger almost than the operating vibration that can be sustained by a traditional platter. Your shock resistance is very similar. Again, a solid state drive, no moving parts. It can withstand a lot of vibration and a lot of shock. You can drop. My laptop that I have here actually contains a solid state drive. I dropped it on the floor. I picked it up and shaken it while I'm running a backup, and you'll never see a problem. Actually, I have a small video that'll show you that there's people that do a lot more to that than you just shake it. The reliability or endurance, a solid state drive has a typical mean time between failure of over 2 million hours. Okay, your standard, even your best SATA drives today have a mean time between failure of under 700,000. Okay, so 700,000 is if you get 700,000 hours out of a typical SATA drive, you're doing really well. Okay, so that's double, nearly triple on the solid state side. Okay. One thing that does another negative, so to speak, of a solid state drive is what this graph is showing you here is the number of I/O operations on the x-axis, and on the y-axis is the transfer size, or your I/O size. Down here is a 0.5 kilobyte, 1 kilobyte, 2 kilobyte, 4 kilobyte, up to 1,024 kilobytes or 1 meg. As the I/O sizes grow, the number of I/Os per second that can be sustained by a solid state drive grows closer and closer to those of your traditional spindles today. As you'll see in some of the numbers that I'll show you here as we get through the presentation, traditional spindles today typically would be recommended and can still outperform your solid state drives or flash drives for large sequential I/Os, which you see a lot of for particular types of operations in a database platform. Random I/Os, however, the solid state drive blows it out of the water. So some of the trends in the industry today that benefit solid state technology or flash technology. The one on the top should be fairly obvious, the green movement. Every corporate data center is under pressure to move to more green data centers. Power consumption needs to be shrunk because power costs are going up, cooling costs are going up. So the temperature of the systems you want to cool needs to be shrunk. Everything about data centers today, 75 to 80% of the costs of a data center over a 5-year term are typically related to power and cooling. So a lot of people think that upfront building a data center, power and cooling aren't much of a consideration because your big costs are the location, building the facilities to support 24/7, 365 operations, and then obviously filling it with all your hardware. Over the life of a data center, the power and cooling consumption will far outgrow the costs of your upfront purchases. A trend for SSD is just the sheer amount of data that people and companies are storing today. It used to be 3 to 5 years ago. I've been working with SQL Server for 10 to 12 years. It used to be that 3 to 5 years ago, if somebody told me they had a 1 terabyte size database, they were in the top 50 in the world on SQL Server. Today, if you tell me you have a 1 terabyte database, you're probably not in the top 50%. To give you an idea of some of the scale, I'm going to be working with a customer starting in 3 weeks that stores 3.5 petabytes of data. So that's 3,500 terabytes. And that's not even the largest SQL Server deployment in the world. So just the sheer amount of data and the sheer number of, you talk about things like YouTube and Facebook and things like that, where people are continually sharing data, wanting to stream media content of all kinds and all types. That takes a lot of storage. And as that storage goes up, they want the response time to remain the same. It's very hard to make a 3.5 petabyte database perform the same as a 3.5 terabyte database, and even harder to make it perform like a 3.5 gigabyte database. So storage bottlenecks or I/O bottlenecks are likely becoming more and more frequent as that data size goes up. Mobility, obviously, like we mentioned earlier, the world is moving towards everything on your mobile device. Those all run solid state and flash technology. Tiered storage is something that developers sometimes aren't aware of, administrators or storage architects typically are. It's a relatively new concept, probably within the last 5 years at least, where it's become quite mainstream. Nearly all major storage vendors today supply a tiered storage solution. And the whole idea is to store your most frequently accessed, most recent data on a smaller number of expensive fast drives so that you don't have to purchase 3.5 petabytes worth of 15K SAS drives. Instead, you can purchase for a lot of the data that is accessed infrequently or historical data that simply needs to be archived. You can store it on cheaper, more dense SATA drives that are cheaper, and you can buy a single spindle that will store up to a terabyte or more of information. So that tiered storage is all about moving data down your tiers from your expensive fast drives to your cheaper dense drives. It's currently estimated by IDC and some Gartner estimates that there's a 75-25 split between performance optimized and capacity optimized storage today, meaning 75% of storage today is performance optimized storage, meaning they'll pay more money to get a fast drive, even though they don't need either all that space or maybe all the performance that'll give it. 25% is capacity optimized, meaning they want to save money to store more information while sacrificing some performance, some throughput. It's expected to flip completely around in the next 2 to 3 years. So 75% will be capacity optimized, 25% performance optimized. And then one thing that doesn't typically strike people as an obvious factor is connectivity. So particularly with things like personal laptops, mobile devices, and whatnot, as the usage of broadband, and we talk about the Web 2.0 world today, Web 3.0 is already underway. As that increased usage of broadband and storage in the cloud and distributed services goes up, there's a lower requirement for large amount of storage on my laptop. 5 years ago, if you told me that I would have a laptop that had 64 gigs of storage and that would be plenty for me, I would probably laugh at you because I would have needed 100, 200 gig storage space on my laptop just to store the things I needed to give presentations or do my work, let alone my MP3 files and videos and all the things that I want. Today, I've got a 64 gig solid state drive and I have about 30 gig free. I have a small external USB drive that stores about 200 gig of information, and it has all the things that I access maybe once every 6 months. So let's map this stuff to SQL Server. So up to this point, we've talked a lot about traditional applications and traditional performance, I/O performance for not only commodity hardware, but also enterprise app dev type platforms and the types of I/O that they will perform. For SQL Server and most any database platform or server, the I/O usage is almost completely opposite. Database servers, SQL Server in particular, attempt to do everything possible to perform small numbers of I/Os with large sequential operations. So if SQL Server has the option, if there's 100 pages of dirty data in cache that needs to be flushed to disk, if those 100 pages are contiguous on disk, SQL Server will perform one I/O operation that's a large sequential write, as opposed to 100 small random operations. The reason for that is, even today with solid state, sequential operations can be finished faster. So like I told you earlier, your traditional applications would sacrifice latency and throughput for a higher number of I/O operations because you usually perform large numbers of small I/O. And you want that response time as opposed to maximizing your throughput. Well, database servers are all about reading and writing data. That's what they do. So they want to sacrifice number of I/O operations for maximizing the throughput of the storage device. The database server is going to push the limitations of any storage device to its limits much more than any traditional application would. If you think of things in SQL Server, when you think of checkpoints, read-aheads, and the way that SQL Server or most database servers work, they're completely geared to small number of IOs as sequential as possible. If you write data to SQL Server, so if you do an insert, update, or delete, how many people think that that piece of data is actually flushed to your data files when you commit that transaction? It's not. It's sent to your transaction log, but it doesn't go to the data files when you finish that operation. It stays in cache. And then about every minute, or depending on how you configured your server, a background process comes along and sweeps through the buffer pool and the cache in memory and takes those dirty pages and pushes them to disk. And it'll sweep through and actually reorder pages so that they're more contiguous, so it can perform smaller numbers of IOs in a larger sequential fashion. Read-ahead is just the opposite. If you have a data warehouse, hopefully it doesn't happen on your OLTP system, though it does frequently, but in a data warehouse scenario, if you've got to run a large query and join two large fact tables together, so 10 million row fact table, 10 million row fact table, you need to join the two together and return all rows. SQL Server has a mechanism referred to as the read-ahead mechanism, which will basically go ahead of the relational join and pull data into cache as fast as possible using large sequential IOs to try and keep the CPU busy. The CPU was processing the request, and every time it needed new data, sent out a request to the IO subsystem to return that data and wait for it to come back. Your CPU would never approach 20% capacity because your storage system is always going to be slower than your CPU. It's just the way it is. So again, most things are geared towards performing small number of I/O operations in large sequential patterns. The other issue with SQL Server is that those four types of patterns that we talked about, random reads, random writes, sequential writes, SQL Server has to be able to perform all four of them very well, or any database server. Why? Because Microsoft doesn't know how you're going to deploy SQL Server. Are you going to deploy it as a data warehouse, as a relational data warehouse? Or are you going to deploy it as an OLTP system? Both of those systems have drastically different I/O patterns. A data warehouse will typically have large reads and scan lots of data, whereas your OLTP system, you want to perform small I/Os very frequently, more closely resembling your traditional application usage patterns. And of course, the other issue is that SQL Server is also dependent not only on some things like the types of data that system supports or the distribution of that data, but also things such as fragmentation of the data, the way that a particular user deems to configure the system, or the way that a particular user chooses to write a T-SQL statement even, can have drastic impacts on how SQL Server can and does perform I/O. Even the editions of SQL Server perform I/O differently. Enterprise Edition is more aggressive about trying to flood the I/O system because the assumption is made that the Enterprise Edition of SQL Server will be deployed on systems that have more advanced, larger I/O systems. Whereas it's also assumed that the Express version will most likely be deployed on smaller systems with smaller I/O subsystems. And that's generally true. So in the next couple slides, I'm going to show you some results of some tests I've done. I'm comparing your traditional hard drives to solid-state drives in regards to SQL Server I/O operations. Now, some of these I/O operations would also map to traditional application usage. The most frequent for traditional application usage would be these top two, 8K random reads and 8K random writes. Now in SQL Server, random writes would happen for checkpoints and interaction with TempDB. Random reads would occur with like index seeks on an OLTP system, small lookups of small amounts of data, or if you have heavily fragmented structures. Okay? The more fragmentation introduced into your system, the lower the chance that SQL Server will be able to sequentialize that I/O. Why? Well, because the data isn't contiguous on disk. Fragmentation is the opposite of contiguous. Okay? So here's all. Anyway, I won't go through all of them, but we're going to go. The tests that I've done, and that I'll show you here in the next couple slides, were performed on 4 different systems in each of these types of I/Os and patterns. The largest one being a 1 megabyte sequential read, which is typically what the type of I/O pattern that your backup operations will perform. The 64 to 256 are mostly bulk operations, could be bulk reads or bulk writes. These 8K, again, these are the ones that would be similar to your applications for more like OLTP type activity. So the 4 systems that I use. I use my laptop, which is sitting right here. It has 2 2.2 gigahertz Centrino processors that each have 800 megahertz frontside bus and 4 meg of L2 cache. 4 gig of RAM is running Vista Ultimate x64, and for storage it has a single 64 gig solid state drive. My desktop I use, which is a quad core 2 gigahertz, much larger CPU system, much larger memory, 16 gig of memory. It has 2 local drives, one 10K drive for boot, one 7.2K drive for data. And then I've got 2 servers. Server 1 is a small to mid-range server, quad core, 16 gig of RAM. It's attached to a Dell MD1000, which is a direct attached storage unit. And behind that, it's got 2 LUNs that have, in total, 14 SATA 2 7.2K drives in a RAID 5 configuration. And then my higher-end server is an 8-core, 3 gigahertz server, 24 meg of L2 cache, with 32 gig of RAM, and it's attached to an HP EVA 6100 SAN. Very expensive SAN. It's got a log LUN with 8 15K SAS drives for an RAID 10 configuration, and in total, 40 15K SAS drives in a RAID 10 configuration for data. Okay, so you'd obviously expect this server to completely demolish my dinky little laptop that's sitting up here giving you a PowerPoint presentation right now. While this server is probably churning through queries from people that are making a lot more money than I am right now. And then, of course, you would probably expect them to work their way down as we go through it. That's a little fuzzier than I was hoping, but I'll walk you through some of the things. From what we've talked about, we would expect solid-state drives would outperform traditional spindles on random operations, particularly random reads. It's a little fuzzy, but you can see here, this is my laptop. In the test, it performed 2,836 IOs per second, totally demolishing my desktop and the small to mid-range server. The high-end server performed just under 5,000 IOs per second. So my laptop performed half of what that high-end server that cost about 600 grand compared to my, I don't know how much I paid for this, 2,200 bucks maybe. So you can see the cost per gigabyte here, 227 for my laptop versus $1,847 for that high-end server. Now, of course, there were some scenarios where things worked out as expected. Sequential writes. Like I mentioned, I think, briefly earlier, solid-state drives still lag behind This will also be included with the CDs or on the website that you get. It comes back live in the next few minutes. I'll gladly finish, but it'll also be up on my blog if you jot it down on my blog address, or you can email me. But basically, the last two couple slides basically just reiterated a lot of what we talked about, which was solid states lag behind a bit sequential writes and really demolish systems when it comes to random I/O access. So the next slide I was going to show you was some tests against a very fragmented system. So if you have a system like an OLTP system and you're not able to defragment it, but you know it's fragmented for whatever reasons, or if you don't even know it's fragmented and don't have a SQL Server database administrator that's able to even tell you if that's the problem or not. The higher levels of fragmentation, the less sequential I/O that SQL Server is going to be able to perform. So typically your performance for large range scan type operations are going to suffer. Most storage vendors today, your big ones, Dell, HP, Hitachi, etc., all have high-end and mid-range storage platforms, direct attached storage systems, and SANs that come with solid-state and flash configurations. So it's right around the corner in terms of when it will be available to mainstream enterprises. Obviously, you can already get it in most commodity hardware. I have a laptop up here that hopefully still works, and probably everybody has a cell phone in their pocket that contains it. My battery is plugged in. I did have a video. The one video I was going to show you was a person that was basically holding two laptops, one that had a traditional spindle and one that had a solid-state drive. They showed a boot up. They hit the power button on both of them. They were both running Vista, might have been an XP. The solid-state drive machine boots in about 32 to 33 seconds, and the traditional spindle drive boots in double that, 1 minute and 10 seconds. The next test they did was opening a 24 meg PDF file, which would be a large sequential read operation for the first time it's loaded. The solid-state system opened it and had it ready to be used within 2 or 3 seconds. It's my machine. It's not that. It's my machine. And the traditional spindle system took well over 15 to 16 seconds to load up that large data file. The next one, which is the one I really wanted to show you, was the vibration testing, which basically two laptops were placed on a vibrating machine, and it measures the vibrations in terms of hertz. And the solid-state drive continued to operate. They had some graphic running, and the traditional spindle you see cracked out at about the number that was listed there. I think it was 3 hertz. The solid-state drive continued to operate even after the machine reached the peak vibrating capacity, which I think was 1,000 hertz. It was still running long. So that was actually the one that I was hoping to show. But, with that, since I can't seem to get my laptop back up and running, any questions?
What about the reliability of flash drive?
Sorry.
Compared to the reliability compared to the spindle drive.
Reliability
Yeah.
of solid state versus spindle. I can't remember what the numbers were, but the mean time between failure for a traditional solid state or flash-based system is about 2 million hours. Contrast that with your traditional hard drive, which is about 700,000 hours or less, which means that typically, on average, by 700,000 hours of use, you'll see a failure on your traditional spindle, whereas on a solid-state system, barring when you're given a presentation, you'll get roughly 2 million or more hours of use of it on average. So much more reliable, the flash system. It basically, the major contributor there is the fact that there's no moving parts in your flash system. So nothing to really break.
So in the current system, if you are running OLTP, so we'll say the RAID 10, which is better, RAID 10 or solid state?
RAID 10 or, I'm sorry, what was the other one? Solid state. Okay, so if you have, the question being using traditional spindles in a RAID 10 configuration or solid state. Also, it's not a black and white question, so to speak. There would be some configuration of traditional spindles where it might be, it's going to depend on your workload, but say you have 10 spindles, 10 15K SAS drives, RAID 10 together. Maybe that would match a single solid state in terms of random item performance. Maybe it'd be 20, maybe it'd be 30. It's going to depend a lot on your workload, the system, et cetera, but there's going to be some number there where as you RAID 10 or any RAID configuration, as you add spindles, it'll start matching what a solid state will give you. The biggest thing to measure is the cost of those, whether it's if it's 2 SAS drives, then you should go with 2 SAS drives most likely. Because I think you can get 4 SAS drives or 5 SAS drives now for the same price of a single solid state. Your RAID configuration would have a impact on it. RAID 0 versus RAID 10 versus RAID 5, RAID 50, et cetera, and the number of SAS spindles or traditional spindles that it would take will differ based on a variety of things. But personally, if I have the option between today an OLTP system that I know performs a lot of random I/O, purchasing a solid state or flash-based system versus a traditional spindle system, I'm going to purchase a solid-based system, at least for my tier 1 data, meaning maybe the last 60 days of data or something like that. Anything beyond that, it doesn't make sense to use a solid state for. One other interesting thing is a lot of people, or a lot of the flat enterprise solid state systems today still need to be rated in some form because even though they outlast traditional spindles by a wide range, people don't want to bet their entire company on it. The interesting thing is RAID 5 or even RAID 6 or something like that on a solid state backed system is going to outperform, or it's going to perform exactly the same as if you RAID 10 those same solid state spindles. Just that's drastically different from it. If you're working with traditional spindles, most of the time a RAID 10 configuration will outperform, at least on writes, your RAID 5, the same number of spindles in a RAID 5 configuration. It doesn't hold true on solid state backed spindles. There's absolutely no reason to do anything other than something like RAID 5 or RAID 6 perhaps, if you're using solid state, because you're going to get higher storage capacity and the same exact response. So that's another interesting consideration to keep in mind. To get the same level of performance from a RAID 10 system, you obviously have to buy more spindles, as opposed to a RAID 5 solid state. It kind of brings solid state more in line with the storage capacity, because cost of storage is still pretty high for solid state. Any other questions?
Is there any operation which the traditional one outperform the solid state drives?
So the question is there any operation where the traditional spindles outperform solid state? And the answer is yes. Sequential writes today, most traditional spindles will outperform a solid state spindle, particularly as you approach larger sequential write sizes. So if you do a 64K or 128 sequential write, it might be about even. As soon as you start getting into 128K or more sequential write operations, your traditional spindles will beat most solid state drives, in a one-to-one competition today.
And in the results, what are you have shown? The processing speed for the server, the process speed seems to be of 8 core, whereas the solid state you mentioned dual core.
It was my laptop with dual core.
So, the more the processing speed, will there be significant improvements in performance?
So it's a good observation, a good question. So the question was in terms of the test that I ran. Obviously, the higher end server had 8-way clocks with 3 gigahertz, enterprise class systems. I think it was 32 meg of front L2 cache, et cetera, et cetera. versus my little dual core. My tests were all I/O bound, or geared towards forcing I/O operations as opposed to giving benefit to the fact that the enterprise class system had much more cache and much faster CPU. I actually, in the data that I'll include, I'll have it in a work spreadsheet, so an Excel spreadsheet. There's actually two tabs. One where I forced the operations to be a max DOP of 1, meaning only a single processor could be used for all operations, and one where it was max DOP of 0. Obviously, when we're talking about solid state and traditional spindle, we're talking about I/O. That has nothing to do with, obviously, I'm not trying to stand up here and say that my laptop would run your enterprise system better than that system on the right. Because there's other factors on day-to-day things. It's not just I/O, because this system could hold 32 gig of data in cache, whereas my laptop can only hold 4. It could run 8 things in parallel at the same time, and I could only run 2 at half the speed. So in terms of overall system throughput, the one on the right would have blown my laptop out of the water, no questions asked. But the test that I ran, I basically would run a test, flush the cache, run a test, flush the cache, run a test, flush the cache. But I was forcing I/O. If I were to, I think in some of the fragmentation tests, I actually compared cold cache versus warm cache. Obviously, the 3 systems on the right blew my laptop away on warm cache scenarios because there was no I/O occurring at all. So good question. Okay, any other questions? Well, sorry to cut it short, but I think my battery ran out and my power isn't working, so feel free to contact me at the address that was on the screen or on my blog, and I'll be happy to reply. Otherwise, have a good rest of the week and a good night.
Thanks.